Okay, folks, today we're going to continue with our discussion of acids and bases. In particular, we're going to talk about how we express numerically the strength of acids and indirectly bases by discussing pH. pH runs from, and I'm sure this is review, the scale for pH runs from technically 0 to 14. 7 in the middle is considered neutral. From 7 to 14, that's increasing basicity. 7 to 0 is increasing acidity. Can there be pHs below less than 0? Yes. pH can be less than 0. Can I have a pH that's greater than 14? Yes, I sure can have a pH greater than 14. This is a logarithmic scale, and because of that, it can go higher and lower. The small letter P in front of an H, or something we'll talk about in a moment, POH, but this prefix P just means you take the negative log of a number, okay? So the way I calculate pH is the negative log of the H plus concentration, or a more authentic or a more real way of putting it is the negative log of the hydronium ion concentration. Because remember, this is real, okay? We don't have H pluses floating around in water. pH literally stands for, in French, pouvoir hydrogène, which literally stands, or literally translated means hydrogen power. So that's where the term comes from. And if 7 is neutral, okay, and going this way is more acidic, this way is more basic, and again, your typical scale is 0 to 14. Battery acid is typically a pH of about 0. Your stomach fluids, which help break down your food, those were usually about 1, a pH of 1. Lemon juice, if I could spell, lemon juice is about 2. Tomatoes, they're acidic. They're about 4. Wine is about 3.5, has a pH of about 3.5. Vinegar is about 2.5. Coffee is acidic. Black coffee, well, I mean all of it, but obviously I'm talking black coffee has a pH of about 5. Whatever you would add to it would change to it, or change the pH. Milk is about 6 to 6.5. Pure water is neutral at 7. Blood is slightly basic. Blood, I think, is about 7.5. Don't quote me on that, but it's around there. Seawater is considered basic. It's about 8. A solution of baking soda or sodium bicarbonate is about 8. Detergents, things we use to clean our clothes and clean things is about 10.5. Bleach. Bleach is another basic substance. That's about 12. Trying to think of anything else. Things like antacids that we take for heartburn. I think if I remember correctly, antacids are about 10 as well. So just the various pH of various normal household items. So we've talked about, something like hydrochloric acid goes into water and becomes H3O positive and leaves its little anion of chloride behind, and it dissociates, okay? Goes into its ions. Literally, the HCl breaks up into H plus and Cl minus, but the water, being very polar, quickly jumps up here and grabs this to become H3O positive, okay, which is where this comes from. This doesn't want to hang around in solution by itself. It's just too positive, it's too reactive. But acids and bases are not the only things that do that. Believe it or not, water auto-ionizes. That's the term, auto-ionizes. So water literally breaks up into OH minus and H plus. Now, a lot? No. It's a very, very, very small amount. Very small amount. But it does do this. Okay, it is something that water undergoes naturally. The reaction for it, the chemical reaction for it, is 2H2O. Breaks down into H3O positive and OH minus. Again, it's to a very small degree. And in water, at 25 degrees Celsius, we have this constant that we call the Kw, which is the water ionization constant, okay? And we come up with it literally by taking the concentration of hydronium ions at 25 degrees Celsius, because this Kw changes depending on the temperature, and the OH minus concentration. You multiply those together, that value is 1 times 10 to the minus 14. So these have to be very, very small. Really, each one of them has to be 1 times 10 to the minus 7th in molarity to equal this number. So that's 0.00000, that's 5, 6, 7 molarity, okay, is your H3O positive and your hydroxide ion concentration. So as you can see, the amount of water molecules that break down is very, very small, relatively speaking. But it does occur, and it does affect pH. Folks, this is why our pH range, which I told you is a logarithmic scale, is 0 to 14. Because if I take the log of 1 times 10 to the minus 14, what do I get? 14. So this is a pH is an easier way, so we don't have to deal with numbers, with huge negative exponents. It's just an easier way to explain and express things. If Kw is equal to the hydronium ion concentration times the hydroxide concentration, and if it's 1 times 10 to the minus 14, okay? And remember, our pH range, it's a logarithmic scale, is 0 to 14, okay? For, very concentrated acids or very concentrated bases, it can be below 0 or above 14. Keep that in mind. And if P is simply means negative log of something, if pH is the negative log of my hydronium ion concentration, then because that lowercase p just represents a numerical activity you perform on a number, I can also have POH, which would literally mean the negative log of the hydroxide ion concentration. Keep in mind, we typically use the pH scale. That's what's accepted. However, because of the math and because of the logarithmic scale, if I take pH and I add to it the POH of a number, I should get 14. So how do I use this? Let's say I want to know what is the pH of a 0.050 molarity solution of HNO3. Okay? If pH is nothing more than the negative log of the hydronium ion concentration, or I could say the negative log of the H plus concentration, well, my concentration is 0.050. So to calculate the pH of this solution, I'll take the negative log of 0.050. Okay? Remember, those brackets mean concentration and molarity. If you do that, your answer comes up to be 1.30. And that, of course, represents an acidic solution. But remember, if P is just a mathematical expression, I could also ask you, what is the POH of 0.050 molar NaOH? POH is going to be the negative log of the OH ion concentration, which I know it's up here. Negative log of 0.050, we really just did it, is 1.30. So the POH of this solution is 1.30. That doesn't give me the pH. Remember I said pH plus POH equals 14. So to get the pH, I could put pH plus 1.30 equals 14, or the pH would be 12.70, and I could see that that was a basic solution. I can also use pH to calculate the concentration of a solution. I could say, what is the molarity of a solution of hydrobromic acid that has a pH of 4.4. You know that pH is equal to the negative log of the H plus, or the hydronium ion concentration. I know what the pH is. The pH is 4.4 equals negative log of that hydrogen ion concentration. Okay? If I take (10 to the negative 4.4, and I take 10 to the negative log of H plus over here, opposite operations, On this side, I'll just be left with H plus. On the other side, I get 4 times 10 to the minus fifth. And of course, this is molarity. So here is my unit. This, of course, was an acidic solution. This is a huge simplification of pH, but all that we'll go into this year, but we'll do problems and practice this in class. So hope you found this useful.